First problem. So we're given the following model for population dynamics. The rate of change of the number of population is equal to negative n times n minus 1 times n minus 3. There's another equation up there that's not particularly useful, but it is kind of what it looks like before you factor it out. And so the first problem says to sketch f of n and use the graphical method to find the steady states, aka equilibria, of the system and their stabilities, meaning stable or unstable. So I want to graph this thing. I don't really want to do a great job of graphing. I just want to do a fine job of graphing. So I know that from here, my intercepts are n equals 0, n equals 1, n equals 3. And since they all have an exponent of 1, we know that each of these is going to cross the x-axis. So, or the horizontal axis. So I really just need to figure out if it's like positive up here, negative up here. So if I pick a number between 0 and 1, like 1/2, it's a negative 1/2 times a negative 1/2 times a negative something. Negative, negative, negative is going to be positive. Negative. Negative times negative is negative. So we know we're going to be negative here. And then we can say it's going to look like this. Cross there, cross there, cross there. Whoops, there. All right. So that's what our graph looks like. And we know that if the graph is above the horizontal axis, that means the things on the horizontal axis are getting bigger because the rate of change is positive. And when it's down below, things are getting smaller. And then when it's above, things are getting bigger. And then when it's below, things are getting smaller. And again, this is right 1. So it should be pretty clear to us that at n equal to 1 is unstable. I guess, I mean, the problem did say to find the steady state. So I suppose we should say not just that it's unstable, but is an unstable equilibrium or an unstable steady state. Whereas both n equals 0 and n equals 3 are stable equilibria. So that would be the answer to part A. That's it, right? This one's unstable because if you're just a little bit off of it, you're shooting out away from it. And both of these are stable because if you're a little bit off of them, you get pushed back towards that, that equilibrium. Okay. Stop me if you have questions, write something in the chat, speak up, but I'm just gonna keep going because there's a few things to get through here. So the second part of this question was to sketch n of t versus time for the initial conditions, n of 0 equals 1.2 and n of 0 equals 0.8. So we're gonna look back at this graph before we start sketching over here and say, okay, if we start at 0.8, oh, sorry, 1.2 is the first one, we're gonna get pushed closer and closer and closer and closer to 3. We're not actually going to get to 3, right? Because if to get to 3, you'd have to start at 3, right? It's a whole thing. But the idea is basically we're going to get closer and closer to 3 asymptotically. So if we start at, say, 1.2, what's going to happen is we're going to get closer and closer and closer and closer and closer to n equals 3. Something like that. And if we start at, and let's use this one in green, if we start at, say, n equals 0.8, which is over here left of one, we're going to get pushed towards 0. So we start at 0.8, we're going to get pushed down like that to 0. That's kind of the whole story. There's not much else to say. Drawing these graphs is fully dependent on looking at what happens if you start at 1.2 or what happens if you start at 0.8 and say, oh, I get pushed in a certain direction. I would definitely, if you have a question like this, I would definitely draw these little arrows on the horizontal axis. What are these problems called? I would say, so these are problems definitely from chapter 7.1 and 7.4, where you're, I forget, I think you're using I think this is still called using the phase plane. I can double check just to be sure. Yeah, we're modeling with differential equations. And then specifically in section 7.4, yeah, we're really using the phase plane to kind of see what's going on here. The difference between this and what we've been doing more recently is that this is just one differential equation, where what we're doing currently is a system of two differential equations. So that's kind of the difference. So the phase plane for this is much easier. Yeah. Where you graph. Yeah. Okay, let's look at the next one. Next one's a bit long. So there's a whole lot of words we got to read here. The drug is introduced to a patient's bloodstream by a bolus injection, meaning all at once. Let's say times 0. X1 is the amount of drug in the patient's blood. So that's X1 is drug in the blood. And X2 is the amount of drug in the soft tissue. Okay. And so then here's what it says. Assume that the rate at which the drug is absorbed from the blood by the kidney and excreted in the urine is 0.2 times X1. So we're not going from the blood to the tissue, we're going from the blood out the body. That's going to be 0.2. I don't know why I'm using red, I just said it. And then let's see, the next thing it says is the rate at which the drug is absorbed from the blood by the tissue is 0.2 X1 as well. So this is going to be 0.2 X1 here. I feel like these numbers were made so that if you accidentally made a mistake, it would still be not, you wouldn't mess it up. The rate at which the drug is reabsorbed from the tissue to the blood is 0.1 X2. And the rate at which the drug and the rate of drug loss from the tissue through enzymatic degradation is 0.1 X2, meaning it's leaving the body, just dissipating. So there is our compartment diagram. And now our compartment model, whatever you want to call it. And now we're going to write our differential equations. So how is X1 changing? Well, we usually want to write the X1s first. The X1s are in red, and definitely the ones in red are the ones that are leaving that one. So we're going to be losing a 0.2 X1 and a 0.2 X1. So we're going to have a negative 0.2 X1 minus 0.2 X1. And then what's coming into it, 0.1 X2. So we have a plus 0.1 X2. For X2, the X1 is going into it. So we're going to have a plus 0.2 X1, but we're losing both a 0.1 X2 and a 0.1 X2. I don't really, sometimes I write 0.1, I usually don't though. Okay, now we should simplify this a bit. We should combine like terms. So we really have dx1 dt is negative 0.4 X1 plus 0.1 X2. And dx2 dt is 0.2 X1 minus 0.2 X2. Okay. That, and then to write it in the matrix form, you're just going to take those coefficients and write them up here. So negative 0.4, 0.1, 0.2, negative 0.2. Okay. That's it for that part. I do want to really, really stress, when you have a compartment diagram, it's not all these four numbers that end up in your matrix. You have different numbers that end up in your matrix. Some of them are the same, but some of them are different. So you really have to write it out and think about, okay, for dx1 dt, how is x1 changing? What's leaving x1? What's going into x1? For dx2 dt, what's leaving x2? What's going into x2? Right. The second part, well, actually, there's more than this. Determine the system. Okay. Yeah, so we did part B. We did part A as well. Part C, is 0, 0 a stable or unstable equilibrium? So to determine this, I would probably think about finding the eigenvalues, which is kind of a pain, right? If I write out the eigenvalue equation, it would be negative 0.4 minus lambda times negative 0.2 minus lambda minus 0.1 times 0.2 equal to 0. Definitely isn't going to factor. It's going to be real ugly. Here is where you really, really, really are going to be better off using the trace determinant method. So my trace is negative 0.4 plus negative 0.2, which is negative 0.6. Great, the trace is negative. that means if they're, in fact, you could almost get away with stopping here. You say, well, I know it's stable, right? Because either the eigenvalues are, oh, that's not true. I take it back immediately. If the trace is negative, the part in the square root could still be big enough that it makes one of them positive. So you could have the other thing, a saddle. Let's look at the determinant. The determinant, this is where things are going to be a little bit tricky. The determinant is negative 0.4 times negative 0.2, which is positive 0.08, minus 0.1 times 0.2, which is 0.02. So that's going to be 0.06. Well, that means we can't have a saddle. So it's not a saddle because the determinant's positive. It could be either a stable spiral or a stable node because our trace is negative. So either you're going to have, we could do a little bit more work. You could say, well, I could actually kind of write out the eigenvalues. So my eigenvalues are going to be negative 0.6 plus or minus the square root of negative 0.6 squared. So that's going to be 0.36. Right, is this 0.36 minus 4 times 0.06 all over 2. So the question is this going to give me real or complex eigenvalues? Well, 0.36 minus 4 times 0.06 is positive, right? It's like 0.12. So that means my eigenvalues will be real because my discriminant is positive. And they can't be a saddle, so they both have to be negative. You could also just, right, so that's why I think it's good to kind of look at the determinant. The determinant's negative, you have a saddle. The determinant's positive, it's not a saddle. So we know that they're both negative. So we have a stable. Cool. Again, if you got questions, chime in.
What was in the beginning? It said like x of 1, x of 2 equals 0, 0. What was that to use for?
So that's just saying we know that x1, we know that 0, 0 is an equilibrium, right? For all these linear systems of differential equations, 0, 0 is the equilibrium point. And the question is asking, is that equilibrium stable or unstable? And so to determine that, we found the eigenvalues, just like we usually do. Can I clarify things?
Yeah, that makes sense. Thank you.
Yeah, but typically, I mean, right, usually when someone's asking you to classify the stability of a linear system of differential equations, they're really saying, tell me about what's happening at 0, 0. Is that equilibrium 0, 0, which is the only equilibrium point in the phase plane for a linear system of differential equations, is that equilibrium stable, unstable? Is it a spiral? Is it a node? That's what we're doing when we classify things. We're talking about what kind of equilibrium that one point at the origin is. If we start talking about nonlinear differential equations, then we'll see systems where you have multiple equilibria. It's a little more interesting. Okay, yeah, we got plenty of time this last one. Last one, there's quite a bit, but let's do it. So so I've got the system of equations, dx dt equals x plus 2y, and dy dt. And I feel like I meant to change that to something else, but I might have forgot to. Yeah, oh well, that's life. It'll be fine. Dy dt is 2x plus y. So find the eigenvalues and eigenvectors in the system, write the general solution for the system of equations. Okay, so we've got the matrix 1, 2, 2, 1. We want to find the eigenvalues. So we've got the trace is equal to 2. The determinant is equal to 1 minus 4, which is negative 3. The eigenvalues are negative 2 plus or minus the square root of 2 squared minus 4 times negative 3. if you don't like doing it this way, do it the way you prefer, right? Do find the eigenvalues whatever way you prefer to find them. This is just the way that I find the easiest. This one would probably be just as easy to do it the other way we talked about it. So this is going to be -2 plus or minus the square root of 4 plus 12 is 16 all over 2. That's -2 plus or minus 4 all over 2. So -2 plus 4 is 2 over 2 is 1. -2 minus 4 is -6 divided by 2 is -3.
James,
Yes.
why is there a negative in front of
Because I was not, yeah, good call. There shouldn't be. Because the reason there was a negative there, to be honest, is I'm usually used to thinking of it as negative b plus or minus, right? But the tau is your negative b, so it should just be tau that goes there. Good call, thank you so much. So 2 minus 4 is -2 divided by 2 is -1, and 2 plus 4 is 6 divided by 2 is 3. Good call, thank you so much. All right, so those are our eigenvalues. Let's find the eigenvectors. So I'm going to do it the way I have to. So 1, 2, 2, 1 times xy equals lambda times xy. So if lambda equals -1, I get 1x plus 2y equals -1 times x. So subtracting x, 2y equals -2x, y equals -x. So there's my eigenline. And here's my eigenvector. X is 1, y is -1. For lambda equal to +3, same idea, 1 times x plus 2 times y equals 3 times x. Subtracting x, you get 2y equal to 2x. You get y equal to x, which is your eigenline. And you get your eigenvector is 1, 1. Okay. Also, I do think it's kind of nice to just write this instead of writing a -1 here and then writing all again and writing a 3 here. If you can just say, oh, if I put a -1 here, I can see what the first equation is. And if I put a 3 here, I can see what the first equation is. So that totally works. And then the general solution is going to be x of t, y of t equal to, this guy is dead, c1 e to the lambda 1 times t times v1 plus c2 e to the lambda 2 t times v2. That would be your general solution without being given the initial conditions to find c1 and c2. All right, so now they're asking us to classify the steady states. So everybody should be able to tell me, since one eigenvalue is negative and one eigenvalue is positive, our steady state or our equilibria is what? Is, yes, thank you, a saddle. Awesome. Okay. So now we want to draw the, so I was very specific about how we wanted to draw this phase plane. So draw the eigen lines of the phase plane. So the eigen lines are, let's see, y equals -x for lambda equals -1. So here's the eigenline, y equals -x for lambda equals -1, and y equals x for lambda equals 3. For the negative eigenvalue, the arrow should, so here's what's special about the eigenlines. The eigenlines, all of the direction field arrows point exactly in the direction that's in the line. So all of your arrows are exactly pointing this way. And since this eigenvalue is negative, right, they all point towards the origin. On the other hand, this eigenline has a positive eigenvalue, so all these direction field arrows are pointing outward, away. So that's what that looks like. And then any trajectory, so like if you start somewhere here, right, you're going to end up doing something like this, or like this. And you start here, you do something like this, and so on and so forth, right? So not that you have to draw all these, but this is kind of the idea. Specifically, if our initial condition is 1, 0, so if we start right here, what's going to happen? Well, we're going to get pushed kind of this way. Okay, I know that seems kind of like maybe too simple, but that's really it. If we started somewhere maybe over like maybe, I don't know, like here, say the point like, I don't know, let's say just for a counter example, if we started at the point 2, -1, right, we would have done something like this. Okay. So the slope of the lines matter. Here it looks like the lines are the same. Yeah, so the slope of the lines it does matter, Max. It's coming from the eigenvectors, right? The slope of this line is -1 because you're literally going 1 in the x direction and -1 in the y direction, over 1, down 1, over 1, down 1. Here, the slope is +1 because you're going over 1, up 1, over 1, up 1. But if you have like, if your eigenvalue was like 2, 3, right, it would have a different slope. The slope would literally be 3/2, right, over 2, up 3, over 2, up 3. Okay, let's get this finished here because we're almost out of time. So the second part of this question asks you to graph x and y versus t. So meaning do the thing where you have, here's t, and I'm going to graph x and y. So if I start here at the point 1, 0, if I start at the point 1, 0, that means x is 1. So the x graph is going to start at 1, and it's going to get, well, it doesn't get big very fast, but then it gets big, 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 right? Because we're moving further to the right. So the x value starts at 1, kind of slowly starts to take off, but then it's going to get really big. Which makes sense, right? Because this is definitely, right, it's exponential growth. I almost said decay, exponential growth. So there's x of t for this initial condition. And if we start at y equals 0, right, because that's where the y value is starting at the point 1, 0, y is 0. The y values get big really fast, and then they actually kind of slow down. I mean, I don't know. You could argue a bunch of different ways here. So the y values are going to get big. Like that. I don't know which one's getting bigger faster. They're probably actually pretty close to the same. So I would probably, if you had to draw x and y, I would probably draw them on different graphs if you had the choice, just so that you wouldn't have to worry about do they cross somewhere or not. On the other hand, just as a counterexample, if we started at the point 2, -1, so if x started at 2, the x values actually get smaller for a minute and then get bigger again. So they probably do something like, I don't know, let's say they get small as like 1.5. So they go down to like 1.5, and then they get bigger again. And if y started at -1, right, the y values just get bigger and bigger and bigger and bigger and bigger. So that's what that's what the trajectories of x of t and y of t, or that's what x of t and y of t would look like on their own graph. The last question here, if our initial condition is 2, 2, draw the trajectory of x of t, y of t. So if we start at 2, 2, oh man, darn it. I meant to do the one that was on the negative eigenvalue, but I screwed it up. Sorry about that. Did I screw it up, or did I screw up my graph? No, that's right. Oh well, I knew I meant to change something. So we started at the point. So let me ask the question I really meant to ask. If we start at the point 2, -2, what's our trajectory? Well, if you're on an eigenline, your trajectory is just the direction of the eigenline. So this is going to take us straight to the origin. What's special about this trajectory is that even though we have a saddle, which normally is unstable, no matter where you start, there is one line of stability. So if you start on the eigenline here, that has the negative eigenvalue, you're gonna end up getting shot towards the equilibrium. Is there anything else I want to say about this? No, not really. All right, it's 2 o'clock. That's all I got. Hopefully that was illuminating. I'll post up the video so you guys can watch it again later if you want to. Got office hours tomorrow at 11, office hours on Friday right before your test at 10, and then as usual after class. I do have office hours right now as well. So if anyone wants to ask more questions, feel free to come to office hours. That's a good question, Jillian. If you're so if we start at the point 2, 2, I think that's actually a good question. So it still is exponential, right? Because your system of equations is still this system here. Basically, what's happening if you're starting at 2, 2 is that this ends up being, 2, negative 2. I apologize. Start at 2, negative 2. This coefficient ends up being 0. Right? So if I had a 2 here and a 2 here, negative 2. I would just get C1 equal to 2 and C2 equal to 0. So then if I start at that point, right, my system of equations is essentially just x equals 2e to the negative t and y equals negative 2e to the negative t. So what's going to happen is that, right, x is going to start at 2 and it's going to just get, right, it's going to look like 2e to the negative t. And y is going to start at negative 2, so that's x of t. Y is going to start at negative 2, and it's going to get closer and closer to 0, because again, y of t was negative 2e to the negative t. So yeah, usually for a saddle, everything blows up as you go to the right, because most of the time you're blowing up. But if you happen to start on the eigenline that has the negative eigenvalue, then everything's just going to get smaller, 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 or closer and closer and closer and closer to 0. You're welcome, of course. Yeah. Hope you guys do well on your test.